Comprehensive Report on Rocket Lab, Past, Present and Future. Introduction. Rocket Lab has emerged as a significant player in the aerospace sector, particularly in small satellite launch services. This report delves into the company's history, its current operations and future aspirations, highlighting the evolution of both Rocket Lab and the Air Force Research Laboratory AFRL Rocket Lab, which has been influential in rocketry innovation. Past, the roots of Rocket Lab. Early developments. The origins of Rocket Lab are intertwined with the early advancements in American rocketry, particularly through the efforts of the AFRL. Initially known as the Air Force Rocket Propulsion Laboratory, it played a pivotal role in developing key missile technology, including the XLR-87 engine, which evolved into the LR-87 engine used in the Titan Intercontinental Ballistic Missile ICBM. The Titan program began with the first successful launch in 1959 and entered service in 1963, marking a significant achievement in U.S. missile technology. To improve missile readiness, the AFRL pioneered the transition from liquid oxygen LOX and rocket propellant 1RP1 to nitrogen tetroxide NTO and Aerosine 50, allowing for storable propellants that could be loaded and launched more efficiently. This innovation was crucial for the Titan II ICBM and its successors, leading to advancements that would shape future rocket designs. Transition to modern rocketry. In the decades following the Titan program, the AFRL continued to innovate. Initiatives such as the Integrated Powerhead Demonstration (IPD) showcased the first full-flow staged combustion engine, while the Upper Stage Engine Technology (UST) program aimed to modernize outdated upper stage engines. The Hydrocarbon Boost Demo HCB program focused on enhancing LOX/RP1 engine capabilities, particularly in light of geopolitical factors that necessitated a reduced reliance on foreign technologies. The establishment of Rocket Lab in 2006 marked a new chapter in modern rocketry. The company quickly gained recognition for its Electron rocket, which became the second most frequently launched U.S. rocket. This achievement laid the foundation for Rocket Lab's reputation in the small satellite launch market. Present, Rocket Lab's current operations. Achievements and innovations. Rocket Lab has solidified its position in the aerospace industry with a series of successful launches and technological advancements. The Electron rocket, designed for small satellite deployment, has completed numerous missions showcasing reliability and efficiency. As of early 2025, Rocket Lab has launched over 58 missions and deployed more than 200 satellites for a diverse range of customers, including commercial, civil defense, and academic sectors. In addition to the Electron, Rocket Lab is developing the Neutron rocket, a larger, reusable launch vehicle aimed at supporting future satellite constellations and significant missions. This expansion reflects the company's commitment to evolving alongside the growing demands of the space economy. Collaboration with AFRL. The AFRL continues to be a crucial partner for Rocket Lab, providing access to advanced propulsion technologies and expertise through public-private partnerships (PPPs). Programs such as the ARMR and TRSA emphasize rapid engine development and responsive space access capabilities. The AFRL's focus on rotating detonation rocket engines (RDRE) presents a potential paradigm shift in propulsion technology, promising greater efficiency and payload capacity. Future, vision and goals. Strategic initiatives. Looking ahead, both Rocket Lab and AFRL have ambitious plans to shape the future of space exploration and access. The AFRL aims to significantly reduce the development timelines and costs associated with new rocket engines through its ARMR initiative, targeting a 70% reduction in development time and 50% in costs. This initiative seeks to leverage modular engine designs and advanced materials to enhance performance and responsiveness. The TRSA program is designed to enable rapid and responsive space access akin to utilizing unmanned aerial vehicles (UAVs) for tactical missions. By integrating advanced propulsion technologies with responsive spacecraft, the AFRL aims to create a system capable of launching and operating in space on demand. Rocket Lab's future aspirations. Rocket Lab is poised to expand its capabilities further with the Neutron rocket. This large reusable vehicle is designed to address the needs of future satellite constellations and significant missions. With a focus on simplifying access to space, Rocket Lab aims to cater to a variety of sectors including commercial, civil, and defense. In addition to its launch services, Rocket Lab is enhancing its spacecraft solutions, providing comprehensive offerings that span satellite design, manufacturing, and on-orbit management. This holistic approach positions Rocket Lab as a leader in the evolving space economy. Conclusion: the journey of Rocket Lab from its inception to its current status as a vital player in the aerospace sector reflects a rich legacy of innovation and collaboration. With strong ties to the AFRL, the company is well positioned to navigate the challenges and opportunities of the future. As Rocket Lab continues to push the boundaries of space access and technology, its impact will undoubtedly shape the next era of aerospace exploration and commercial spaceflight. Timeline of key events: 1954 to 2005, development of the Titan ICBM and advancements in rocket propulsion at AFRL. 1994 to 2006, demonstration of the first full-flow staged combustion engine through the IPD program. 2004, initiation of the USAT program to modernize upper stage engines. 2007, launch of the hydrocarbon boost demo program. 2017, AFRL's focus on ARMR and TRSA programs begins. 2006 to 2023, establishment of Rocket Lab and evolution from the Electron's first launch to the development of the Neutron rocket. As Rocket Lab and the AFRL continue to innovate and collaborate, the future of space exploration and satellite deployment looks promising, with exciting developments on the horizon. Counterintuitive information identified in the content. 1. Public-private partnerships, PPPs, and innovation. While one might assume that government-funded organizations like the Air Force Research Laboratory AFRL operate independently and solely focus on national defense, the content indicates that AFRL's Rocket Lab has significantly benefited from collaborations with private companies through public-private partnerships, PPPs. This partnership model has allowed private companies to leverage AFRL's advanced technologies and expertise, demonstrating that government entities can play a facilitative role in enhancing private sector innovation rather than being solely top-down institutions. 2. Transition from military to commercial focus. The historical narrative suggests that the origins of Rocket Lab are deeply rooted in military applications, particularly in developing ICBMs. However, the present scenario shows a shift towards commercial applications, particularly with the Electron rocket and its focus on small satellite launches. This transition from military to commercial focus may seem counterintuitive given the historical context of military-driven space technology development. 3. Detonation-based propulsion. The exploration of rotating detonation rocket engines (RDRE) presents a radical departure from conventional propulsion methods, which are typically based on deflagration subsonic combustion. The idea that a detonation-based propulsion system could yield better efficiency and payload capacity may seem counterintuitive, as detonation is often associated with explosive and uncontrolled reactions, whereas traditional rocket engines are designed for controlled combustion. 4. Complexity of simplifying access to space. The narrative around Rocket Lab emphasizes simplifying access to space through innovations like the Electron rocket and the upcoming Neutron rocket. However, the underlying complexity involved in achieving such simplifications, including advanced engineering, rigorous testing, and the need for extensive regulatory compliance, highlights a paradox where making something appear simple may involve intricate and complex underlying processes. 5. Enhanced performance from toxic propellants. The historical development of the Titan ICBM, which transitioned from LOX/RP1 propellants to nitrogen tetroxide/Aerosine 50, showcases a move toward more toxic and corrosive propellants for the sake of performance and launch readiness. This trade-off between safety and performance may be counterintuitive, as one would typically prioritize safety in aerospace endeavors, yet the operational readiness and reliability of the ICBM system warranted this choice. 6. Rapid development timelines. The future goals of the ARMR initiative aim to significantly cut down engine development timelines by up to 70%. This ambition challenges the traditional aerospace industry norm where lengthy development cycles are the standard due to the complexities and safety requirements inherent in rocket technology. The notion that such drastic reductions in development time can be achieved while maintaining safety and reliability defies conventional expectations. 7. Simultaneous launch capability. The TRSA initiative aims to create a capability for simultaneous launches within a 24-hour window akin to calling upon UAVs for missions. This presents a counterintuitive challenge, as the complexity of coordinating multiple launches, including logistics, regulatory compliance, and safety considerations, would suggest that such an operational model is impractical. Yet the narrative suggests that advancements in technology and partnerships could make this a reality. In summary, the content reveals several counterintuitive insights about the evolution of Rocket Lab and the broader aerospace industry, particularly in terms of collaboration, technology application, and operational strategies that defy traditional expectations. In exploring the comprehensive report on Rocket Lab's past, present, and future, there are several key aspects that are often overlooked yet hold significant implications for the industry and broader space exploration efforts. Below are some important details that merit deeper examination. 1. Public-private partnerships (PPPs). One of the most significant yet potentially overlooked aspects of Rocket Lab's current operations is its extensive collaboration through public-private partnerships (PPPs) with various commercial entities. This collaboration is not merely a financial or logistical arrangement. It represents a strategic shift in how advanced propulsion technologies are developed and integrated into modern launch vehicles. Significance: the integration of government and private sector expertise accelerates innovation and reduces the time and cost associated with developing new technologies. This model provides a pathway for rapid transition of military-grade technologies into commercial applications, fostering a dual-use technology environment. Furthermore, it may lead to increased competition in the launch market, which could drive down costs for satellite deployment and expand access to space for smaller players. 2. Rotating Detonation Rocket Engines (RDRE). The RDRE program is another critical area of focus that may not receive the attention it deserves. This propulsion technology represents a radical departure from traditional rocket engines utilizing detonation instead of deflagration for combustion. Significance: RDRE's promise to significantly improve efficiency and payload capacity. Their potential to reduce engine mass could lead to lighter and more capable launch vehicles. This technology could set a new standard in propulsion, enabling more ambitious missions including deep space exploration and potentially manned missions to Mars. The implications of RDRE technology extend beyond just performance. They may redefine engineering approaches in rocketry and challenge existing paradigms. 3. Tactically Responsive Space Access (TRSA). The TRSA initiative aims to create a framework for rapid and on-demand space access, akin to calling for unmanned aerial vehicles (UAVs) for military operations. This concept represents a shift toward a more agile and responsive space capability. Significance: the ability to launch missions on short notice could be transformative for military operations and national security. In a world where time is often of the essence, the capacity for quick deployment of assets in space could provide strategic advantages. Moreover, this concept could facilitate humanitarian missions and rapid scientific responses to global events, showcasing the dual-use capabilities of space technology. 4. Affordable Responsive Modular Rocket (ARMR). The ARMR program's objective to cut engine development costs and timelines by significant margins is a remarkable goal that is often overshadowed by the excitement surrounding new rocket launches and missions. Significance: if successful, ARMR could democratize access to space by making it more financially viable for a greater number of companies and countries to develop and launch their satellites. This could lead to an increase in the number of active players in the space economy, fostering innovation and competition. Additionally, the modular design could allow for customizable solutions for various mission profiles, enhancing operational flexibility. 5. Historical context and legacy of AFRL. While the report covers the technological advancements and current projects, the historical context of Rocket Lab's operations through the lens of the Air Force Research Laboratory AFRL is often underappreciated. The legacy of the Titan ICBM and the evolution of propulsion technologies over decades illustrate a continuous thread of innovation that has shaped modern rocketry. Significance: understanding this historical context enriches our appreciation of current advancements and highlights the importance of foundational research in shaping future technologies. It serves as a reminder that today's innovations are built on the shoulders of past achievements, emphasizing the need for sustained investment in research and development. 6. Integration of space systems technologies. Rocket Lab's ambition extends beyond launch vehicles to encompass a wide range of space systems technologies, including spacecraft design, satellite components, and on-orbit management. Significance: this holistic approach to space access signifies a trend toward integrated solutions in the space economy. As the lines between launch services and satellite operations blur, companies that offer end-to-end solutions may have a competitive edge. This could also streamline operations for clients who benefit from a single provider for multiple aspects of their space missions, ultimately making it easier and cheaper to access space. 7. Sustainability and reusability efforts. Rocket Lab's ongoing efforts to improve the reusability of its rockets, particularly with the Electron and the upcoming Neutron, are noteworthy but often overshadowed by the race for larger payloads and more powerful rockets. Significance: the push for reusability is crucial for reducing the cost of launches and minimizing the environmental impact of space missions. It reflects a growing awareness within the industry regarding the sustainability of space operations. As the space economy expands, the need for environmentally responsible practices will become increasingly important, and companies that prioritize sustainability may lead the market. Conclusion: the report on Rocket Lab encapsulates a dynamic narrative of innovation and collaboration in the space sector. However, the significance of certain elements, such as public-private partnerships, advanced propulsion technologies like RDRE and ARMR, the historical legacy of AFRL integrated space systems, and sustainability efforts, are pivotal to understanding the transformative potential of Rocket Lab and similar entities in shaping the future of space exploration and utilization. Recognizing these details not only highlights the complexity of rocket development but also underscores the multifaceted nature of the evolving space economy, where innovation and collaboration will define the next era of exploration. 1. Historical development of rocket propulsion technologies. The past section highlights the significant contributions of the Air Force Research Laboratory AFRL in the development of rocket propulsion technologies, particularly through the evolution of the Titan ICBM and its engines. The transition from liquid oxygen/rocket propellant 1-LOX/RP1 to nitrogen tetroxide/Aerosine 50 propellants illustrates key advancements in missile technology that not only improved performance but also operational readiness. This legacy of innovation laid the groundwork for the contemporary landscape of space access and satellite deployment, demonstrating how historical advancements continue to influence modern rocketry. 2. Public-private partnerships and technological transition. The present section emphasizes Rocket Lab's collaboration with private companies through public-private partnerships (PPPs), which have been instrumental in transitioning advanced propulsion technologies to the commercial sector. The Integrated Powerhead Demonstration (IPD) and Upper Stage Engine Technology (UST) programs showcase how these collaborations have fostered innovation and enhanced the capabilities of new space launch vehicles. This approach not only benefits private companies by providing access to cutting-edge technologies but also strengthens national security and the overall space economy. 3. Future innovations in rocketry. The Future section outlines ambitious initiatives such as the Affordable Responsive Modular Rocket ARMR and the development of Rotating Detonation Rocket Engines RDRE. These projects represent a paradigm shift in propulsion technology, promising significant improvements in efficiency, cost reduction, and rapid responsiveness for space missions. The focus on developing modular, reusable systems is particularly relevant in today's context of increasing demand for launch services and the need for sustainable space exploration practices. By positioning itself as a leader in these innovations, Rocket Lab is not only shaping its future but also influencing the broader trajectory of the space industry. For Rocket Lab's comprehensive approach to space systems, Rocket Lab's evolution from a small satellite launch provider to a comprehensive space solutions company encapsulates its strategic vision for the future of space access. With the development of the Neutron rocket and a diverse range of spacecraft technologies, Rocket Lab aims to simplify and democratize access to space for various stakeholders, including commercial, civil, and defense sectors. This holistic approach not only addresses the complexities of launching payloads into orbit but also enhances the potential for innovation and collaboration across the space economy, paving the way for new opportunities in space exploration and utilization. 1. NASA's Apollo program 1961–1972. The Apollo program was a landmark series of missions undertaken by NASA, culminating in the first successful manned moon landing in 1969. This program showcased advancements in rocketry, spacecraft design, and human spaceflight. The Saturn V rocket, which was developed during this era, remains one of the most powerful rockets ever built. The program not only achieved profound technical milestones but also had a significant impact on international relations and the space race, setting the foundation for future exploration. 2. SpaceX's Falcon 1 and Falcon 9 programs 2002-present. Founded by Elon Musk, SpaceX has revolutionized the aerospace industry with its Falcon 1 and Falcon 9 rockets. Falcon 1 was the first privately developed liquid-fueled rocket to reach orbit in 2008, marking a significant achievement in the commercialization of space. Falcon 9 further advanced this by introducing reusability with its first stage landing, drastically reducing the cost of access to space and enabling a new era of satellite deployment and cargo missions to the International Space Station ISS. 3. The V-2 rocket development 1944. The V-2 rocket, developed by Wernher von Braun and his team during World War II, is considered the world's first long-range guided ballistic missile. It marked a significant advancement in rocket technology, demonstrating the potential for space exploration and military applications. The technology and knowledge gained from the V-2 program laid the groundwork for post-war rocketry efforts, including the U.S. space program and the development of subsequent launch vehicles like the Redstone and Saturn rockets. Future outlook: Rocket Lab, past, present, and future. As we look ahead to the future of Rocket Lab, several key trends and developments in the space industry and technological advancements are likely to shape the trajectory of the company and its contributions to space exploration and commercialization. 1. Expansion of launch capabilities. Rocket Lab's development of the Neutron rocket signifies a strategic pivot toward larger payload capacities and more complex missions. The Neutron, designed for the deployment of satellite constellations and interplanetary missions, positions Rocket Lab to compete in the growing market for large satellite launches. This expansion is expected to open new revenue streams and establish Rocket Lab as a key player in the rapidly evolving space economy. Predictions: increased launch frequency. With the Neutron rocket expected to become operational, Rocket Lab may achieve a significant increase in launch frequency, potentially surpassing its current capabilities with the Electron rocket. Diverse payloads. The ability to launch larger payloads could attract a wider array of clients, including governments, commercial enterprises, and international organizations. 2. Advances in propulsion technology. The Air Force Research Laboratory AFRL is actively working on innovative propulsion technologies, including the Affordable Responsive Modular Rocket ARMR and Rotating Detonation Rocket Engines RDRE. These advancements are set to revolutionize space access by making it more efficient and cost-effective. Predictions: enhanced efficiency. Future rockets incorporating RDRE technology could deliver higher thrust-to-weight ratios, leading to reduced launch costs and increased payload capacities. Faster development cycles. The ARMR initiative aims to streamline engine development, potentially reducing timelines and costs by up to 70%. This could accelerate the introduction of new launch vehicles into the market. 3. Responsive and on-demand launch services. The concept of tactically responsive space access (TRSA) will likely gain traction, allowing for rapid and flexible responses to emerging space needs. This capability is particularly vital for military and defense applications, where timely access to space can be critical. Predictions: on-demand launch capability. Rocket Lab may offer on-demand launch services that enable rapid deployment of satellites in response to real-time intelligence or urgent needs. Integration with defense strategies. Increased collaboration with defense agencies could lead to new contracts and partnerships, enhancing Rocket Lab's standing in the defense sector. 4. Integration of space systems and services. Rocket Lab is not just a launch provider, it is also positioning itself as a comprehensive space systems company. The integration of satellite design, manufacturing, and on-orbit management into their offerings will likely redefine their business model. Predictions: end-to-end solutions. By providing complete end-to-end space solutions, Rocket Lab could dominate niche markets, especially in small satellite deployments and custom satellite solutions. Collaborative ventures. Partnerships with other aerospace companies and governmental agencies could facilitate the development of innovative spacecraft technologies and services. 5. Sustainability and the commercial space economy. As concerns about space debris and sustainability grow, Rocket Lab's commitment to responsible space operations will become increasingly important. This includes efforts to ensure the safety orbiting of satellites and reducing the environmental impact of launches. Predictions: sustainable practices. Rocket Lab may pioneer practices in sustainable space operations, such as developing reusable rocket components and implementing effective end-of-life strategies for satellites. Regulatory compliance and leadership. As regulations around space operations tighten, Rocket Lab could emerge as a leader in compliance and sustainability, enhancing its reputation and marketability. 6. Global market reach and partnerships. The increasing demand for satellite launches globally presents an opportunity for Rocket Lab to expand its market reach. This will entail establishing partnerships and launch sites in strategic locations worldwide. Predictions: international launch sites. Rocket Lab may establish additional launch facilities outside the U.S., particularly in regions with burgeoning space industries such as Europe and Asia. Collaborative projects, joint ventures with international space agencies and commercial partners could enhance Rocket Lab's technological capabilities and customer base. Conclusion: in summary, the future of Rocket Lab is poised for growth and diversification. With advancements in propulsion technology, an expanded launch portfolio, and a commitment to sustainable practices, the company is well positioned to play a vital role in the next era of space exploration and commercialization. As technology evolves and demand for space access continues to rise, Rocket Lab's innovative solutions and strategic initiatives will likely shape the future landscape of the aerospace industry.